Hey everyone, and welcome to Gradient Daily. Today, we are diving into a really fascinating paper from Peking University and Microsoft Research Asia called Diffusion as Self-Distillation. This paper goes after a huge inefficiency that's right at the heart of models like Stable Diffusion. You know, these incredibly powerful image generators, they're kind of like a Frankenstein's monster, cobbled together from three separate models that were all trained at different times. So this paper asks a simple but profound question. Can we just get rid of all that complexity? Can we build one single unified network that's not just simpler, but actually better and way more efficient? Well, the answer they came up with could really change how we build these things in the future.
So here's our roadmap for today. First, we're going to pinpoint exactly what's wrong with the way we do things now. Then we get to the real mystery. We'll look at the obvious fix and why it fails so spectacularly, a phenomenon the authors call the Great Latent Collapse. The key to cracking this case comes from a really brilliant new perspective, looking at diffusion through the lens of self-distillation. And once we get the real problem, we can walk through their super elegant solution, check out the amazing results, and then wrap up with a look at what this all means moving forward. All right, let's dive right in. To really get why this paper is such a big deal, we gotta pop the hood on a standard latent diffusion model, or LDM, like Stable Diffusion. See, it's not one single thing. It's actually a system of three totally distinct models, all trained separately. First up, you've got an encoder. This thing takes your beautiful, high-res image and squishes it down into a much smaller, more manageable latent space. Think of it like creating a super detailed compressed blueprint of the image. Second, you have the diffusion model itself. This is the artist, the part that actually learns to generate new stuff, but it only works with those little blueprints. And finally, you have a decoder, whose only job is to take the final blueprint and blow it back up into a full-size picture. This three-part pipeline, it works, but as we're about to see, it is far, far from perfect. So this whole three-part design, even though it gets the job done, comes with some serious baggage. First off, it's just not unified. You know, the big trend in AI right now is toward these massive single foundation models, things like vision transformers that can do it all. LDMs, with all their stitched-together pieces, just feel clunky and old-fashioned by comparison. Second, this separation actually hurts performance. The autoencoder part is trained to do one thing, compress and reconstruct images perfectly. But the diffusion model has a totally different goal, make cool new images. They're not working together. The autoencoder doesn't know what the diffusion model needs to be creative, and the diffusion model is just stuck with whatever it gets. And finally, there's a huge efficiency cost. That autoencoder can eat up a full 20% of the model's total parameters and adds a real lag time when you're trying to generate an image. It's like having to fire up a separate clunky generator just to get your main engine started. And this brings us to the core mystery of this paper. See, the authors wanted to fix this whole three-part mess by just unifying everything into one network. But what they found was that the most obvious, logical way to do that leads to an absolute, total, catastrophic failure. I mean, it's the first question you'd ask, right? If the whole problem is that you have these three separate pieces, why not just smash them together? Just build one big network and train the whole thing end to end. Let all the parts talk to each other and optimize the whole system together. It seems like the simplest, most obvious solution in the world. Well, because when you try that, this is what happens. And this graph is the smoking gun. It is a complete disaster. Look at the orange line. That's the reconstruction loss. You want that to go down to zero. But it just flatlines. The model isn't learning anything. Now look at the blue line. That's the effective rank, which is basically a measure of how much information is in the latent space. And it plummets instantly to 1. Think of it this way. A high rank space is like having a huge vocabulary to describe the world. A rank of 1 is like trying to write a novel using only the word V. It means the encoder is taking every single image, a cat, a car, a mountain, and mapping it to the exact same single point. It's a total information blackout. The authors gave this epic failure a fittingly epic name, Latent Collapse.
So let's really nail down what we mean by latent collapse. It's this tragic state where the model's internal brain, its latent space, just loses all ability to express anything. Its dimensionality completely vanishes. Imagine you have a massive library, but instead of organizing the books neatly on shelves, you just throw every single one into a giant single pile in the middle of the floor. That pile is a collapsed latent space. All the books are technically there, but it's completely useless. You can't find anything. You can't create anything new. So this is the central mystery we have to solve. Why does adding the diffusion process, which is supposed to be creative, cause the model to just give up and create this useless pile of information?
And to solve this mystery, the authors had an absolutely brilliant aha moment. They realized that if you kind of squint and look at their failing models sideways, it looks a whole lot like another famous method from unsupervised learning, self-distillation. And that connection, that simple reframing of the problem, is the key that unlocks this entire puzzle.
So what the heck is self-distillation? Well, in popular methods like Dino, you have a student-teacher setup. You've got two identical networks. One is the student, which is learning super fast, updating on every single training step. The other is the teacher, which is a much more stable, slowly evolving copy. Think of the teacher as a wise old master. It doesn't update with every new piece of information the student learns. Instead, it takes a tiny fraction of the student's new knowledge and slowly averages it into its own vast experience. This is called an exponential moving average, or EMA, and it makes the teacher incredibly stable. The goal is for the student to predict what the stable teacher would say. And here's the kicker. This whole teacher-student dynamic has a mathematically proven, built-in mechanism to prevent collapse. That's the critical piece of the puzzle.
Okay, this one diagram from the paper basically tells the entire story, so let's walk through it. Over on the left, in A, you've got standard self-distillation. A student learns from stable teacher. This works great. Next, in B, is our standard latent diffusion model. The encoder is frozen solid, and the diffusion model learns. This also works, but it's inefficient. Now, look at C. This is our failing model. And here's the insight. It's basically a broken version of self-distillation. The encoder is trying to be both the student and the teacher at the same time. It's an unstable teacher that's changing its mind every single second. No wonder it collapses. And finally, over in D, we have their solution, DSD. They just fix the broken parts to make it look like the stable setup from A again. It's so elegant.
So, looking through this new self-distillation lens, the authors identified two specific culprits, two bad guys responsible for the collapse. The first is latent variance suppression. Basically, when they looked at the math, they found a hidden signal in the loss function that was telling the encoder, hey, whatever you do, make your outputs less diverse. And the model, trying to be a good student, just took that to the extreme and squashed everything to a single point, zero diversity. Boom, collapse. The second culprit is a failure of rank differentiation. There's a rule in self-distillation that says, for training to be stable, the student needs to be a low-pass filter. It needs to learn the general gist of things, not the noisy, fine-grained details, like summarizing a book, not memorizing it. But in the naive setup, we ask the diffusion model to predict the noise. And noise is, by definition, the highest frequency, most detailed signal possible. So the task was literally telling the model to do the exact opposite of the one thing required to keep it stable. So now that we have this perfect diagnosis, the authors could switch from being detectives to being engineers. They didn't need to guess or use some random hack. They could just systematically go in and neutralize each of these two root causes, one by one, to build a system that actually works. All right, let's tackle culprit number one, the variance suppression. The problem was this destructive signal being sent back to the encoder. The solution? Beautifully simple. They just cut the wire. In the code, this is an operator called stop gradient. It acts like a one-way valve. The signal can go out, but nothing can come back. It's like putting up a tiny little roadblock on the information highway that says, nope, you destructive gradient, you can't go back this way. This instantly shields the encoder and lets it build a rich, diverse latent space.
So did that fix it? Well, kinda. The data here shows what happened. The collapse is much, much slower. But you can see that the blue line for effective rank still eventually drops, and the orange loss still flattens out. It still collapses. This is such a crucial result because it tells us we're on the right track, but we've only solved half the mystery. We've slowed the bleeding, but we haven't stopped it. We've only taken care of one of our two culprits.
Okay, on to culprit number two, that whole rank differentiation mess. The problem was that predicting random noise is the wrong kind of task. So they just changed the task. Instead of telling the model, find the random static we added to the TV screen, they told it, find the original clean TV show that's hidden inside the static. Now, mathematically, these two things are equivalent ways to denoise an image. But, and this is the critical part, for training stability, they are completely different. Predicting a clean, structured image is a low-rank task. It forces the model to act like that low-pass filter we needed to find the signal in the noise. And just like that, this simple change in what the model predicts brings everything back in line with the rules for stable self-distillation.
So now, let's put all the pieces together to build the final DSD framework. First, you've got the decoupling. that stop gradient that prevents the variance from being crushed. Second, you have the loss transformation, predicting the clean image instead of the noise. Those two are the essential fixes that prevent collapse. But then, to really push performance, they went all in on the self-distillation playbook. They added a proper, stable EMA target, that wise old teacher, for the student to learn from. And finally, they threw in aggressive data augmentation, which forces the model to learn the real essence of an image, making it an even better low-pass filter. That's it. Those 4 steps are the whole shebang. And you don't have to take my word for it. The proof is right here in these training curves. Look at case 3, with our 2 main fixes in place. And it works. The orange loss goes down, the blue rank goes up, the collapse is solved. Now look at case 4, when they add the stable EMA teacher. The lines get even better, faster, smoother. And finally, case 5, with data augmentation. Another little boost. This step-by-step breakdown is just beautiful science, clearly showing how each piece they added makes the system more and more stable, leading to a perfectly trainable end-to-end model.
So, the theory is solid, the diagnosis was brilliant, and the training is finally stable. But who cares if it can't make pretty pictures, right? That's the ultimate test. So let's look at the results and see what this new unified machine can actually do.
And this is it, the final product. At its heart is one big, powerful brain, a single vision transformer. And this one network does everything. Think of it like a Swiss Army knife. It has different heads, or tools, for different jobs. It has a head for encoding and decoding images, a head for creating the latent blueprints, and a head for doing the diffusion. And that whole teacher-student thing is still here. You've got the online network learning fast, and the target network providing stable guidance. But the key is that all the different learning signals all flow back to update the same shared brain. The clunky, separate pieces are gone, replaced by this one elegant, multi-talented network. And this is where things get kinda nuts. Check out these results. The metric here is FID score, lower is better. Their DSD model has just 205 million parameters, and it gets a fantastic score of 4.25. Now compare that to a big model like MDT. MDT is over 750 million parameters, and it only gets a 6.23. So let me get this straight. The DSD model is less than a third of the size, and it's significantly better? That is an incredible result. This is exactly the payoff you hope for from end-to-end training. By letting everything optimize together, the model just learns to be way, way more efficient.
And I mean, just look at these images. The pictures really speak for themselves, don't they? The detail, the realism, the sheer diversity here, it's all top-notch. These are absolutely state-of-the-art, high-fidelity images, and they were all produced by that one, single, unified, and shockingly efficient model. This is the proof that all that theory and clever engineering wasn't just an academic exercise. It translates directly into incredible generative power. All right, so where do we go from here? This is an amazing paper, but like all great research, it's not the end of the story. It opens up a ton of new questions. So let's take a quick, balanced look at the clear strengths and the big question marks that remain.
Let's be clear, this is a huge step forward. The strengths are obvious. They finally achieved that holy grail of a unified architecture. It's wildly parameter efficient, and the solution is so satisfying because it's based on a real theoretical understanding, not just some random hack. That said, the authors are totally upfront about what's next. The big question is, does this scale? They haven't built a billion parameter version yet to take on the giants. And the other question is it a one-trick pony? We know it's an amazing image generator, but are the representations it learns inside useful for other things like classification? That's still an open and really exciting question for future work.
Okay, let's boil this whole thing down. If you walk away with just 3 key ideas, make it these. First, the problem. The standard 3-part diffusion model is clunky, inefficient, and a roadblock to progress. Second, the insight. Just jamming those parts together causes a catastrophic latent collapse, but you can understand and fix it by looking at the problem through the lens of self-distillation. And finally, the solution, the DSD framework, which uses that insight to build a stable, end-to-end training method that gives us a single, elegant, and super efficient generative model. And this really leaves us with a pretty provocative final thought. What we're seeing here isn't just a small tweak. It's a move away from these specialized, cobbled-together systems towards something far more unified and principled. It connects the world of generative models with the world of representation learning. So the big question is, are we seeing the first real steps toward a kind of grand unification in visual AI? A future where one single, powerful, end-to-end model could be the foundation for everything we do with images? And that's our breakdown of diffusion as self-distillation. I hope you found this as interesting as I did.
If you want to keep up with all the latest research that's shaping the future of AI, you know what to do. Hit that subscribe button. We'll be back soon with another deep dive. Thanks for watching.